Okay, so our final talk of this morning's session will be by Chris Bowman talking on the work of Christine Bessenrodt.
Right, so first of all, thank you very much for the opportunity to speak about Christine with a community that meant a lot to her and that she did a lot of work for. The first time I met Christine was a week of good wine and Kronecker coefficients in Banff, and we wanted to solve a conjecture of Christine's from 1999, which I'm going to tell you about in a little bit. And she had all the big ideas in place before, just on day one. But it took us a year of hard work in order to take care of these intricate details and the case-by-case analysis, which I will not tell you about in this talk. And for me, this was very Christine. On one hand, brilliant and with these big ideas in place, but also this diligent, detail-oriented calculation and hard work. And this hard work and dedication was how Christine approached everything. Running the department in Hanover, her work for the DMV and the European Women in Mathematics, which she co-founded, maybe founded, I can't remember. And she finished the report of her student Adrian's 200-page thesis the week before she passed. So I was at the last pre-COVID conference in Oberwolfach, and Igor Pak said to me that Christine was the only person in the conference that could possibly have understood every talk. And so what I will be talking about today is my own very small view of her work within combinatorial representation theory. And as some of you might know, it would be impossible to discuss all of Christine's work across group theory, Auslander-Ruyten theory, modular representation theory, and algebraic combinatorics. So I've just picked some of the bits that I understand. Okay, so one of the problems that Christine and I worked on a lot together was the Chronica problem. So I'm going to let Sn denote the symmetric group on n letters. And I'm going to let chi lambda C be one of its irreducible characters labeled by a partition. And the Chronica problem, which is old and easy to state, but hard to solve, is can we compute the products of these characters? So if you haven't seen it before, let's look at an example. And S3 is the first non-trivial example. So well, here is the character table of the symmetric group on 3 letters. And I am going to calculate the tensor square of this 2-dimensional character here. Okay, well, I'm squaring things. So what do? You just square all the numbers. So 2 times 2 is 4, 0 times 0 is 0, minus 1 squared is 1. And so lo and behold, here we have a tensor square of this character, easy peasy. Now notice that if I sum all the numbers in this column, 1 plus 2 plus 1, I get 4. If I do 1 plus 0 plus minus 1, I get 0. 1 plus minus 1 plus 1 is 1. And so this is the answer to this problem for this question. Namely, take this tensor square. Every single representation appears exactly once. Okay, so high off of that success, let's see if we can understand anything about this problem. No, we can't. It's really hard. It's one of these problems. It started in 1939 to some extent, and it's never really, we haven't got very far in that time. And so part of Christine's work was somehow looking at these impossible problems, and I've shown you one of them, the Chronica problem, and saying, okay, well, it's impossible. Let's look at milestones of our understanding. And one of the things you can do is classify nice products. And what do I mean by nice here? Well, if a product is irreducible, so A times B is just C, doesn't decompose at all, well, that's nice. Slightly broader class would be homogeneous. So A times B is a scalar times C. And A much harder class, a much more interesting and rich class is multiplicity-free products. And this is one of these questions that appears in a lot of places in a lot of fields. In invariant theory, I believe in invariant theory, it's about commutative endomorphism algebras. In algebraic combinatorics, we find it somehow the limit of what you can know for certain types of question. For example, p-Castaner-Lustig polynomials, we can calculate the ones, well, okay. We can prove Lustig's conjecture for the ones that are multiplicity free. And in this case, algebraic combinatorial problems like Kronecker and Black-Witson coefficients and things like that. So those are the nice products. Another big question that's been coming up recently in this field is, can we detect positivity of coefficients? So this is a complement to the multiplicity-free question. If the first question, multiplicity freeness, was when is A times B a sum of things all appearing with coefficient 1, this question is, so that was throwing away coefficients, being like, I only want 0 or 1 coefficients. This is saying, okay, what if I don't want to know the coefficients? I just want to know if it's non-zero. And then finally, a sort of even harder question is, how do you decompose these products into symmetric and antisymmetric parts? So let's start with the first question. So tensor product of any representation with a one-dimensional character is always homogeneous and simple. There you go. Here's a product with a trivial character, which, as you know, you can multiply every number by 1, it stays the same. And so this character stays the same. And then, okay, there's also the sign character. And as some of you may know, if you take the sign character, you tensor, what you do is you flip in the east-south axes. Well, okay, the east-southeast axis, if you're English, or a different one if you're French or Russian. So both of these are homogeneous and irreducible and easy, right? And we've already seen in our very first non-trivial example involving the first non-one-dimensional representation of the symmetric group, it's not homogeneous. There's 3 of these things, and it's not irreducible. There are 3 of these things. And in fact, what Christine proved with Sasha Kleshev in 2000 is that these are the only irreducible or homogeneous products for Kronecker coefficients. And this is a similar vein of classification theorem, which Christine pursued in other places. For alternating group characters, so restrict from Sn to An, it's alternating subgroup. These were classified in 2000 again. And products with very few, so here this only has 3 homogeneous components. If you say, okay, I'm not just interested in 1 homogeneous component, but maybe 2 or 3 or 4, these were classified by Bessenrodt and Willenberg in 2014. So this is one sort of axis of our understanding of Kronecker coefficients, which is due to Christine, and it's via how many irreducible components appear. Okay, so I said I'd tell you a bit about symmetric and antisymmetric parts. So take this character, square the character, or square the group element. You can do both these things. If you add them up and half them, we call that the symmetric bit. If you do one minus the other and half that, we call that the antisymmetric bit. Let's have a little look here. I'm going to show you the symmetric square of the character we just saw. Okay, so it's going to be 2 squared is 4. The square of the identity is itself, so this is 2 squared plus 2 over 2. Okay, now the next one, 0 squared is this guy. The square of the 2 cycle is the identity, so 0 squared plus 2, take half. Okay, here, if I square a 3 cycle, I get another 3 cycle. So if I square this and add it back and take half, what I get is the character 3, 1, 0. And notice that this is the sum over the first two rows here. So 1 plus 2 is 3, 1 plus 0 is 1, 1 minus 1 is 0. So there's the symmetric square for you. And we said that the whole, from definition, the tensor square is the sum of the symmetric and the antisymmetric parts. And so, well, the antisymmetric bit needs to be everything that we've already seen that wasn't here. Okay, and so in 2022, Christine and I classified the symmetric and antisymmetric Kronecker products which are homogeneous. So for the symmetric ones, it's pretty boring. But the antisymmetric ones, you get the boring one where like, okay, the trivial guy. You also get the standard representation, if you like, n minus 1, 1. A couple of small rank things, which always happens with Kronecker coefficients. And that's everything up to conjugation. Okay. So here's the hardest of the Kronecker problems that I have worked on with Christine. And it's about when can you understand these coefficients? So when do we have nice formulas for Kronecker coefficients? Well, there's a very famous one, which appears in Stanley's book, which says, okay, if I take any representation and tensor it with this standard guy, well, that's the same as restricting from rank n to rank n minus 1, inducing back up, oh, and removing one guy that sort of appears extra that I don't like. And so we can do it in terms of addable and removable boxes, like so. So here, this is going to be my lambda. So if I restrict it, I just remove all possible nodes. So here, I remove that node or that node, and so that is the restriction. When I induce that, I'm going to say, okay, how many ways can I add a node to this guy? Well, there's 1, 2 ways I can add a node to this guy. And for this guy, I can add a node in 1, 2, 3, 4 ways. And so I'm going to take this, I'm going to say, aha, well then what is this tensor product? It's just the thing I had there, but I cross out one of the copies of the representation lambda I started with. So here, this is a multiplicity-free product because, okay, everything appears once now that I've crossed out this guy that appeared twice. Okay, so that's one of the nicest character products formulas. But I have another favorite one. So here, that's nice and easy. Everyone knows how to decompose the tensor product with sign representation with itself. It's just the trivial. Okay, easy peasy. What I'm going to do now is fatten out this rectangle by making it go like this. So I'm going to consider KK tensor square. Okay, well, I'm going to fatten out the original guy that I started with. There's his fat friend. I'm going to add something new which couldn't appear before because the first row is would have been too short. And another guy here. Okay, now let's start seeing the pattern. So in the next one, I see, okay, this increasingly long first row guy, he's always going to appear. Now this guy appears by adding to this one in the first row. This one appears by adding to that one in the first row. But we do get some new stuff, as always. There you go. I am leading somewhere with this. This is going to stabilize in a way. Okay, so now long first row guy. Let's increase him, increase him, increase that one. That's me adding 2 there. And then a couple of other things that crop up. Cool. I think I'm going to stop there because that's quite enough. But what I'm going to do is going to color things in. So notice that, okay, here, what are these partitions in blue? Well, these are partitions which have all even parts. 4 even parts, in fact. So this is the partition 2, 4, 2, 2, 6, 4, 2, 2 cubed. And indeed, you can sort of see these as just, okay, there are 5 partitions of 4, and you just double them all up. Okay, and then what are the white guys? The white guys are the partitions with exactly 4 odd parts. So notice that, okay, 1 squared didn't appear here because 0 is not odd. Okay, those are the odd ones. And so this is an old thing, but from 2010 or so. But Christine and I recently, and Stembridge also noticed, oh, okay, actually, not only is this already a nice formula for the tensor squares of these gray partitions on the left, but actually the symmetric parts, the symmetric part is all the even guys, the anti-symmetric part is all the odd guys, and so it has a nice decomposition as well. So I said that there would be a classification of these multiplicity-free things. Oh, and I should just point out, notice that everything here appears with coefficient 1. You might not notice that because I didn't write 1s everywhere, but such as things. So what we do is we classify these multiplicity-free products. And the list isn't great, it's a bit ugly. It's got the first example I showed you, fine. The second example I showed you and some variants on it from induction and restriction. Some other guys, okay, a 2-rower and a hook, a rectangle and some small partitions, small depth, and some other things. And the point isn't really what is on this list. The point is for everything on this list, there is a formula which gives you exactly the answer of the Kronecker decomposition. And this is somehow, in one sense, one of these axes of understanding. And it's sort of, in one way, as far as we can push it. You can classify the ones with, I think you can classify the ones where the highest coefficient is 2, rather than here where its highest coefficient is 1. But it doesn't get much further than that. So again, Christine conjectured this in 1999, having done a lot of computer cases. She then did a lot of work over it over the years, and we finally proved this classification in 2016. And it involved two lovely ideas that she said, okay, let's set these two off against each other. One is de Vere recursion, which allows you to remove little bits from partitions. And the other is the semi-group property, which was quite new then, and it's due to Manival, which is that you can add partitions and the Kronecker coefficients must increase. And that's a really lovely property. But what I wanted to stress here was, okay, this is a very hard and in some ways ugly classification, which involves a lot of work and a lot of detailed calculation, as well as the big ideas. And this to me is a very Christine sort of theorem, this complement of big ideas, but also incredibly hard, detailed work. And indeed, I said it was a very Christine theorem. Here are some other ones by Christine. So, oh, not the first one. So Stembridge in around 2000, the same time that Christine made the conjecture, looked at symmetric functions and Kac-Moody generalizations. Christine did the spin symmetric functions, the quasi-symmetric functions with Willigenberg, and recently with myself and Rowena Paget, the plethism products of Schur functions. And in Adrian's thesis, 200 pages, remember, Adrian Homer did the products for alternating groups, which is incredibly difficult. So yes, this is a big theme of Christine's work. These, how far can you push a question? How far can you push your understanding? And one of the answers is that multiplicity freeness gives you a way of getting a grip on these otherwise intractable problems. For example, the plethism products are one of the other one from this talk of Stanley's big problems in algebraic combinatorics. So impossible in general can be solved for multiplicity free things. Okay, so multiplicity freeness is over now. We're going to look at a bit at positivity. So here is a very famous theorem of Burnside, which says, okay, given any faithful character of any group, if you take enough tensor powers of it, you will eventually see every character of the group, which is lovely. And a good question there would be, okay, I haven't got time to tensor this off to infinity. How small can M be? Well, we've already seen that if I take this little staircase partition here, 2, 1, and take its tensor square, I see everything straight away. M is 2 here. And what Jan Saxel conjectured is that if I take a triangular number and I take the staircase partition, k minus 1, k minus 2, k minus 3, 2, 1, this sort of thing that looks like a triangle, it's triangular number, his tensor square contains every symmetric group character. So M is 2 is the conjecture. And this is proven to be another one of these milestones in the theory. It's attracted a lot of attention, but seems bizarrely out of reach, even though it's just take this tensor product, this guy times himself, decompose him. You're like, okay, that's just one partition. So rho, rho, lambda for rho this staircase. And we can't do it. And all we actually need to do is detect positivity. And it's somehow, it shows just how hard the Kronecker problem is. And this is a question that really captured Christine's imagination, and she's proposed a lot of generalizations of this conjecture and made a lot of headway on it. And one of the most interesting generalizations she did with Greta Panova, which said, okay, actually, this is very specific. Lots and lots of these guys exist, and they say what they should look like. And this will appear in a paper of Greta's in the summer, I think. So I'm going to come back to that. I haven't really proven anything in this slide, but I'm going to prove something in the next bit. So I said part 1 was about algebraic combinatorics. This is a field that she worked very hard in. Part 2 is about modular representation theory, a separate field, which may not be that popular with the audience, but I'm going to show you how Christine used the ideas from modular representation theory to understand these Kronecker coefficients, which hopefully people do like. So here's a nice example of using 2 modular representation theory in order to understand the Kronecker problem. So here's the statement, very cute. Every symmetric group character of odd degree appears in Saxel's tensor square. Huzzah. So here's an interesting, well, barely interesting little tensor square here, the first staircase that isn't just the one that we looked at earlier. Here are the Kronecker constituents, and I'll go as far as that. Okay, there we go. Everything else is a conjugate, so that's preserved because this is a self-conjugate partition. So this and all its conjugates appearing with the same numbers. So here's the tensor square. Which one of these have odd degree? Well, these 4 have odd degree. These guys are even, but in fact, there's an even more general thing which works because of this nice idea in 2 modular rep theory of character being as odd as possible within its 2 block. And that's called height 0. And okay, this last one is height 0. So here we get everything apart from this guy. He's of oddish degree.
Chris, you know you have about 4 minutes left.
Okay, cool.
Yeah.
And I just wanted to say that, oh, there's this lovely application of this, which came out last week by Harman and Reiber. They actually proved that the tensor cube, so M is 3, is an upper bound by using these modular representation theory ideas. Cool. And then all I want to say here, because I'm running out of time, is that Christine classified, well, no, Christine didn't classify. Christine almost classified the modular representations there when they had were irreducible, and that this was been recently completed by Lucia Marotti, who, like me, also owes a great deal to Christine. So this is another part of Christine's legacy. And it's been very important in group theory due to work of Kleshev, Marotti, and Tiep. And Christine really set Lucia on this path. So I just wanted to point out that. So finally, I wanted to end on a conjecture of Christine. So here we go. Character vanishing. Here's another combinatorial question. you can start with, do products factorize uniquely? So if I take a product of symmetric group characters and another product of symmetric group characters, what if they are just the same? Does this imply that the characters you started with were the same? Modulo silliness, like permuting lambda and mu. For Lie groups, the answer is yes. This was a annals paper by, I can't remember the name of the guy, but the answer is yes. And for symmetric groups, this was asked by Cedric Lecouve, and I was like, oh, great, maybe I'll get an annals paper proving this. But Christine found counterexamples using the idea of character vanishing. And so we were like, okay, well, let's go into character vanishing. So we started asking, when do characters vanish? What are the elements on which a character vanishes? When is it 0? And Christine used this to solve some of Saxel's constituents. And it's also important in modular rep theory, so it's appeared a lot of other places. So I'm going to let V lambda denote the set of group elements upon which the character vanishes. Does knowing V lambda determine the representation I started with? The answer is yes. So here is the table S6, and what I've done here is highlight all the zeros. So here, this character vanishing set, so if I take the character vanishing set to be this pair of zeros here, I color in the 2 columns with these zeros in. Lo and behold, the only things where the character vanishing set is these 2 columns is this guy and his friend, linear twist. Again, here is a character vanishing set for this guy, it's just this column. And lo and behold, when I highlight this column, these are the only 2 rows which have it as its vanishing set. Finally, this vanishing set for this partition is this guy. And lo and behold, only one self-conjugate now partition has this vanishing set. So for symmetric groups, yes, knowing this determines the characters. But we were late to that party too, so this was already solved in 2004. And what I wanted to end it on, and so I'll just state this, it's not very attractive. It's something that says, okay, can we determine when do 2 characters have the same vanishing set? The answer is almost never for the alternating groups, sorry. When do 2 alternating group characters have the same vanishing set? The answer is almost never, unless you're in a very couple of very specific cases involving 3 core and 3 quotient combinatorics of partitions. So this is just a conjecture of Christine's that I wanted to state, regardless of what the details are. It's that almost always character vanishing for alternating groups does determine the character, with some very few exceptions. Okay, thank you very much.
Thank you. Are there questions for Chris?
Chris, have you looked at tensor power? So you have the Saxel conjecture where you have tensor powers of the staircase. Now that should decompose according to, so if you take the D tensor product, then that would decompose according to partitions of D, right? I mean, generalizing the symmetric and antisymmetric part. Has anybody tried to look at how those different pieces would?
Not yet, no, because it's so hard. So it's somehow doing the symmetric and anti-symmetric things adds another layer of difficulty. It makes it worse. And actually, basically no, very little is known.
But the symmetric and anti-symmetric, you seem to know, right? Just for staircases?
No, we knew the symmetric and anti-symmetric for the partition 2-1.
Well, so even that's not.
And for the partition KK. And there's some few other instances, partitions of small Durfee size, things like that. But
not for staircases.
Not in general, no.
Thanks.
Other questions? Okay, well, oh, could I have a reference for Burnside's theorem, says Bruce Westerbury.
It's in his book. So yeah, that's in Burnside's book. I don't know where.
Okay. Let's thanks again for a great talk about Christine's work.